physical design optimization in Synapsys flagship digital implementation product portfolio. And he has various technical research engineering leadership roles across the company, digital physical design tools, and he's also leading the AI machine learning innovation in the Fusion Compiler, flagship product in Synapsys. And he's a recipient of various patents during his career, and more importantly, he was a recipient of the Best Paper Award in DEC 2022 related to reinforcement learning optimization in physical design. The stage is yours.
Thank you for the introduction. Okay, so my talk will be a little different. All this time we have been hearing about the technical topic, deep down into that. And what I am going to present is the perspective from the industry, perspective from Synopsys, as the industry is seeing an accelerated pace of AI innovation, how we are envisioning that, what are the things that are needed for exploring AI and delivering the most superior PPA to our customers. Our customers are extremely demanding and they have aggressive time schedules and we need to deliver PPA. How we fit AI into that model. So in fourth industrial revolution is on us. I don't want to go into the details, but everything that you hear around AI or new AI models like transformers, GPTs, like Internet of Things, blockchain, digital twins, what it all means. It means a huge pressure and huge demand from the semiconductor. Our customers are building much bigger AI chips, with a lot of silicon contents, putting a lot of RTL logics, and there's insatiable appetite for power, performance, and area within a very aggressive time scale. That's what's shaping this industry. That's what the demand from the customers and the EDA tools need to react to that customer's requirement. So that's where we see accelerated space of innovation needed. We are seeing that there is a huge amount of complexities. The complexities of the chip design has gone astronomical. And delivering PPA within a short time has become an incredibly huge challenge. So the EDA workflow definitely has the potential to offer this AI opportunity. Now, it is one of the complex engineering process where the workflow starts from the physical design perspective, synthesis all the way to post-route. And there are many subsystems involved into that. From the floor plan perspective, from the tool options, parameter tuning, from the cell library characteristics, all these things, there is no one size fits all. Different designs have different complexities, different challenges, and this is extremely human-intensive job. Lots of human experts are needed, and lots of manual tuning going over months to deliver PPA for the crown jewel blocks that customers are interested. Right? So that is the current situation, which has already been improved by as many of the Synopsys tools, design space exploration, and optimization, parameter tuning. We have already seen that over a few years, and they are delivering the exact requirements of the customers today. But there's a lot to do, and there's a lot of potential how the EDA tool can transform itself. So as you know that this whole workflow from synthesis all the post-route, it has lots of algorithms that are fitted with NP-complete problems, but we are trying to solve it in a linear heuristic way and in a linear time. Now, these heuristics definitely has lots of hyperparameters, and this creates an enormous search space. This search space is so huge that you can't throw 10, 20 computes and still get to the best of that, right? And this requires lots of human expertise who has a lot of tribal knowledge that is there in order to get to the PPA. And we are seeing that this large search space problem is something that we need to optimize more efficiently and more creatively, more importantly. Especially if you look at, like customers will look at performance and various different metrics. No metrics they are going to leave apart. Area, leakage, power, and all of these are very important metrics for our customers to optimize concurrently in a multi-objective way. So as you can see that industry has already adopted the ability of a black box optimization. So you have tunable parameters, you know that these are the some few things that you're going to explore, and you can run it through the black box optimizations and get the rewards back, fit it into your model, typical reinforcement learning, and you can optimize it. But this black box optimization has its own challenge because this is a huge workflow. The typical blocks, like if you think of our customers, might be running 3 weeks to even complete the physical design flow. And successive iterations and loops in order to optimize your parameters at a customer premise on a real-time block is a significant prohibitive challenge. Right? So the tool itself is so huge and so expensive in terms of turnaround time that you have very limited opportunities for sequential iterations. And also, as you see that these parameters can only be added at the beginning of the tool, and the entire tool is reacting to that parameter only without having the intelligence of changing itself or adapting itself. That's why it's a black box optimization. So what's next for you? So far I told what is the current way that we are trying to solve parameter optimization or trying to explore more people. But that's not enough. In fact, we need to radically change the concept of hybrid model where black box and white box optimization works together. And for example, design learning driven auto convergence. This is very important. Like, you have to learn within the run that you can be smarter. You cannot just say, okay, I will react to what is coming to me from outside. The tool itself needs to get more and more learning driven, and tool needs to ability to self-guide itself when it sees a challenge while it is executing the flow from the beginning to the end. And look at what is our customers asking for. Customers are saying that the industry is suffering from the talent reduction, talent shrink. The EDA experts are also having a talent reduction. By 2030, we may not have enough talents who can actually manually engage to improve PP every block. You need the concept of virtual designer, concept of green designers, and of course expert designers. Out of 200 blocks that a customer is running, maybe only there's a 5% block that requires a human experts to come in and manually use all their tribal knowledge and experience to push the people. But there are green engineers fresh out of college, very limited few years of experience. They should be able to use the tool as efficiently in order to drive people. Virtual designers is just push button. You don't have anybody to do it. There are tons of blocks that are easy. Any extra PPA that you can get out of it, that's where our productivity is. So that's the customers are defining their productivity, how they will manage with their resources, with their pool of blocks. So that brings me to the next slide. And here I wanted to talk about a little bit the solution that I'm trying to propose here and what we are looking for. As a physical design, you see there's a huge amount of subsystems involved in it. All these, many of them are NP-complete problems. Many of them are huge hyperparameters. Now, it's a complex workflow. As you can see that one of the things you will see when you start from synthesis all the way to the end of the flow, same engine runs multiple times. Your sizer runs multiple times. Your buffering, netlist restructuring runs multiple times. Your global routing runs multiple times. Your placement runs in a multiple loops. So it's not that a single subsystem is running one time and you are done. Your detailed placement legalization runs multiple times. So what you learn from a given execution of the life cycle of the flow upfront at a single invocation, and use that learning going forward, because you are learning something of that design at that point of time, and that learning cannot go wasted. So that's one of the key principles. The opportunity to improve from the previous execution, that's what I'm saying, learn from the previous execution. Now, learning from the subsystems, so one of the key things is that what placement has decided to do can influence what optimization or netlist restructuring and netlist synthesis need to do. So the handshaking from the one subsystem to another subsystem, the learning passed down, has also a merit, and we have seen that there is a value to that. So an auto discovery of trend and pattern. So there is very few things that we do when a system is running, when the flow is running, and at the end of the flow, we do not understand what are the trend and the patterns that we have seen in the different subsystems. The concept of auto discovery or auto analysis is very important. That you need to discover the problem before you actually look at the log files, open the block, look at the GUI, look at all your scripts, your reporting commands to understand. But why the flow itself as an agent understand and discover the patterns? Because if it can discover, it can take an action. And that is needed. Because otherwise the flow runs brute force without real-time understanding of the design characteristics and design value. And self-recovery of the trajectory anomalies. Assume that something went wrong. Is there an incremental way to improve from that anomalies, from that trajectory that the flow is, as an agent, is monitoring while the flow is executing? And these are the things that we need to use for an intelligent AI flow that can avoid leaving it to the users and solve the problem right at that time of the execution, or single execution. Next thing that I'm going to talk about is the pilot learning. What I mean about the pilot learning is that you don't need to run a big giant net list to understand the problem. You don't need to run a global sizing on a 5 million instance to understand how this sizing reacting to cell selection, how this sizing reacting to area power problems, how is the cell selection reacting to legalizability. You need to reduce the problem into a small sub-problem, maybe into top 300 timing path violations, just to use that and iterate to understand that can you learn within the tool's execution. So reduce the problem into a smaller sub-problem and reduce the domain such that you can iterate faster, because you cannot iterate on a 5 million instance and do any parameter optimization. It's runtime prohibitive. So how do you make a very small sub-problem like a global route engine and quickly figure out, is there a hyperparameter tuning that is needed in order to fit your routing resources? So think about that. This is how the EDA tools need to reinvent itself. That do your parameter optimization, whether you use a Bayesian optimization, whether it's multi-arm bandit, that's not the point. Point is that can you reduce it into a smallest subset of the problems statement and iterate and optimize and find the sweet spot and use that in the same run. Yeah. So I've just given some examples for the time, like fast solver placement. So when placement is running, it runs multiple solver-based loops. In few of the loops, you can actually find out how nicely the curve fits between the weighted oil length and active oil length, like the high toggle rate oil length. How the clumping causes place power and the oil length trade-offs. So just an example. So these are the things that we need to really innovate ourselves. And wherever you can leverage ML models, we should try to do that and in a very small subsets and use that for the subsequent steps. Okay, so next I talk about the concept of the design deep insights. Now, so far we have been talking about exploration, and the final outcome of the exploration is always a top matrix, like WNS, gross negative slack, total negative slack, density, median clock latency, your total area, total power. But these are coarser metrics. The end of the flow PPA matters to our customers, to our final solution. But as the flow progresses from synthesis all the way, the intermediate subsystems needs to understand what metrics is important to understand its own health. The health metrics are different than the final PPA metrics, because health metrics are like what are the bottlenecks of your timing paths? What are the PPA bottlenecks? Like what kind of bottlenecks that you see in terms of design inside? Is it a macro heavy block, or is it a block that has lots of control logic, like clock and sequential dominated? Is it a kind of block that has lots of channels and the channels are over congested? These design insights needs to be converted into some features. And when you convert them into a feature, as you see, naturally will fit into the concept I call that insights to an insight embedding. So you have the insights, the tool derives these insights as the flow progresses, and these insights can be converted into a categorical levels or a numerical level. And this becomes your embedding. And these embeddings can be created at any phase of the flow so that you can use this for the eventual goal. That is, how do you recommend an action? How do you predict an action? Because this is important in terms of classifying similar designs having a similar insight embedding. And this you can offline understand, train it, you can pre-train, but as you are running the flow on that design, you need to understand this deep insight. You need to procure this deep insight. And what you need is the creativity in terms of building these insights. These insights are not something you will find in EDA tools, just as a report command or just as a top-level course metrics. You need to build a metric that determines the health of that subsystem, that determines the health of the thing that you are trying to accomplish at that stage of the flow. So here I'm showing how design insight-based physical design flow will look like. Right? It's transitioning from the black box AI. It's transitioning into a white box AI now. So as you are running from synthesis all the way to the sign-off, insight embeddings can be captured at different places, and then these insights can be very different. What you have in the beginning and what is happening at the CTS or clock pre-synthesis level, or at the post-route or routing level. They can be all different, but you need to collect these insights because that insight tells you about the design. And as you find that, now you see that how a standard flow converts into a more adaptive and intelligent flow, where these insight embeddings will be actually influencing your decisions. The adaptive decision, whether it's a reinforced decision, these decisions are going to be taken within the flow. So the single flow has to get more intelligent. And now you can try multiple different computes, multiple different runs with different parameters, but at the end, each flow needs to know that it is not a black box. It is not just, it runs only by reacting to the parameters that are set at the top. Okay, so that's what I'm saying, that all these insight embeddings translates into an action prediction, and the tool is going to take this action. Next, I'm going to talk about design insight assisted solution space navigation. So far I've been talking about how a single invocation of the run in a single machine EDA tool needs to get more and more intelligent. But now I'm going to talk about that how the design insights can further be explored and harnessed. Given that you have the design insights, you can actually create a top recipe group prediction for running in the multiple machines, a multiple compute. Right? And this recipe grouping is a technical paper that got accepted in DAC. So I hold on to the details so you guys can see on the DAC paper. The idea here is that the deep insights will influence how we predict the recipes, and this is going to be a fully learning-driven system. Okay, so we have some experimental results on what we have been discussing so far, based on the baseline, based on the human PPA tuning, based on offline prediction and recommendation, and we see some encouraging results from our work. So key takeaway, AI is everywhere, right? You have to build a fully learning-driven system within the EDA tool itself, within the various subsystems. You need to use deep insights, because the deep insights are your netlist similarity, netlist features, and you can harness given similar netlist insights and their embedding. Can we predict actions? Can we predict some high probability actions that can be evaluated and invoked at the time of execution? And then insights inspire AI models to generate action recommendation, and that is what I will show you as the next tool. So this is all about how I see the EDA tools will be reinventing and accelerating AI or PPA exploration that our customers are looking for. We have to deliver PPA with a very aggressive timeline. Any questions?
We can take one quick question. If you have.
Yeah, just one question. I'm curious about what kind of actions, what kind of training you discover the game. Can you be more specific?
Sure. That's why I'm saying. So as you see that when we talk about the actions,
Right.
it's basically that you start learning about the design characteristics. So one of the design characteristics is that is it a control logic block or is it a crossbar type of block, like congestion heavy or non-congestion. Very early in the flow, you can detect whether this design will cause you congestion and what are the congestion parameters that you need to learn, even without customers were telling you that I am a high congested block. Right? There will be different kind of parameters in terms of weighting multi-objective trade-offs. Any multi-objective trade-offs, area power or like delay, these are all weighted systems. Now you can control the weights early in the flow if you know what kind of lighting cell selections. Right? You can have different BT types, BT classifications coming in, and that can take you a very greedy area power trade-off versus another design which does not have this trade-off. So today nobody understands that. They just have a tribal knowledge, try to do things and try to solve the problem.
Thank you.
Because of the time, I believe you can follow up if you have more questions. Thank you very much.